everyone. How we feeling tonight?
Yeah! Woo!
Love to hear. My name is Kevin Xiong, and I'm a second-year mechanical and aerospace engineering student.
I'm Dylan Damnawin. I'm a second-year chemical engineer.
I'm Zachary Lee. I'm a second-year poli-sci student.
I'm Devin. I'm also a second-year chemical engineer.
My name is Ibrahim. I'm a second-year electrical engineering major.
And this is our instrument, the Dynamic Ultralight Beam Sieve, or DUBS for short. Our team wanted to harness the properties of light to create an auditory and visual musical experience. Now, DUBS creates a unique playing sound while still being ergonomic to the user. And although our instrument is very synth-heavy, it still offers the creative expression that a more traditional acoustic instrument would provide. But how does it work? Well, there are three main components to our instrument: the slider, the button panel, and the carousel. To make the slider, we harness a property of light called the inverse square law. As a source of light moves further away, its measured intensity drops. LED here is our source of light, and a photoresistor measures this change in light intensity to calculate a musical note. Similar to how an automaton functions, the slider controls a singular root note that spans 1A to A octave. And now will explain how the button panel functions.
All right. So as you guys might have already heard, the slider only controls the tonic. But what about undernotes? Well, that's where the button panel is for. So the button panel is responsible for three things: additional notes aside from the tonic, changing the octave range, and the waveform of the sound being outputted. So let's start with the front. As you guys might see, there are 12 buttons, each corresponding to the 12 chromatic intervals. Each time a button is pressed, a note is assigned to one of the sensors on the carousel, which will be explained in a bit. When the button is pressed, it doesn't actually make a sound until you crank the carousel. This is similar to like the priming mechanism of a guitar, whereby pressing on the strings of the instrument doesn't actually make a sound until you strum it. Likewise, when you press a button, it doesn't make a sound until you crank the carousel. Moving on to the back side of the instrument, there are three more buttons. Two of them are responsible for the changing the octave of the tonic, or the slider. And the other one is responsible for changing the waveform of the sound being outputted. There are three to choose from: a pure sine wave, a pulse or rectangular wave, and a triangle or sawtooth wave. Now I'll pass it to Devin to talk about the carousel.
Yeah, so the carousel is one aspect of the DUBS, and consists of 4 photosensors, which along the photosensors correspond to notes that we play. And so when the light is positioned towards the top of the carousel, that plays the first note of the chord, and depending on the position of the slider. And the remaining photosensors correspond to the remaining notes of that chord, and is controlled by the buttons held on the button panel. Now, all this can be controlled by the crank on the user's right-hand side, and this allows the user to control the tempo at which they either want to arpeggiate notes or strum a chord. So Zach will demonstrate. Yeah. So now I'm asking on David to talk about the knobs at the top of the carousel.
Of course, so on top of that, we have 3 knobs to control further settings of the instrument. First off, you can control the master volume of the sound output. Secondly, on the triangle and the pulse wave settings, you can adjust the modulation of those waves specifically. So on a pulse wave, you can adjust the duty cycle, and on a triangle wave, you can adjust it to become a sawtooth wave feedback. And lastly, we have our sustain knob, which controls how long a note will mellow out for. Alright, and I'll give it to Matt to discuss the inner workings of the instrument.
All right. So one of the main strengths of our instrument, you guys might have noticed that this instrument is actually being projected into the PA system of this room. That's because our instrument is actually true digital to analog conversion. And this has many benefits. One, you can obviously connect it to any modern sound system you like this PA system. You can connect it to a DAW, play to the DAW. Or if you want some analog filters on your sound, you can connect it to like a guitar pedal. Other things of our instrument include how easy it is to get it to play straight out the box. All you really need is a micro USB power supply, a 3.5mm out, and your sound system of preference, like an amp or whatever you want. And the last advantage of our instrument is that it's very self-contained within the instrument itself. All the computing, hardware, software, all that is on the instrument already. And the computing behind the scenes is very simple. All it takes is an Arduino Mega that controls all the inputs and sends it to a Raspberry Pi, which is responsible for the sound synthesis through a program that's called Pure Data. Now, the Arduino Mega is also responsible for miscellaneous outputs that we also think are crucial to the visual audio experience of the instrument. Everything will explain that.
So as Matt previously stated, we have an Arduino that takes in inputs and digitally processes it. So we output that to both a user interface, like you see on the slide, how that looks. This information shows the output waveform, the button intervals being pressed, the master volume, the root rate frequency, all in real time to help guide the musician. And lastly, we have an LED matrix, which you might have seen already. So every time the sensor is passed through, a random LED pops up. It's more of a cosmetic appeal, but also these LEDs adjust to the settings of the instrument to provide some visual feedback. For example, the color will change with the modulation of the output waveform, and the sustain of each LED will match the corresponding note. And I'll pass it to Zach to talk more about playing with numbers.
Well, there's two main ways to play this instrument. The first one we developed was melodically. So to play melodically,